Yes. Hello, everyone. Today we will have the last lecture in Stockholm, but one before last lecture in the lecture series. And today we'll try to speak about theory of everything, whatever it will mean. And I would like to start to play by playing a small game. So Eduardo, can you share your screen? So if you're in chat, you should have received a link, and if you're in the room, you have a piece of a sheet of paper. You can log into the question form. There you can think about your favorite object. Think about any object you like, and enter its dimensions, mass, and distance. Mass should be in kilogram, and distance should be in meter. How to enter is this example, and you follow the example. Yes, so when you enter your favorite body, it will appear here on the screen. So a person appeared. Okay. So there are two axes. Horizontal axis is the length of object. I'm using logarithmic scale. This means 10 here means it's 10 to the power 10, or it means 10 billion meters. And 20 means, well, 1 with 20 zeros meters. So if you are going to do something small, it will end up being in the center. And in the vertical direction also we have logarithmic scale of mass of an object. So two person. So I challenge you to find something bigger or smaller than a person, significantly. Yeah. Okay, so here we go. So we have Earth. So Earth is much bigger thing. It is something which is according to this picture is it's 10 to the power 24 kilograms and 10 to the power 8 meters. So it's 10 to the power 8 meters is 1,000 meters, 1 kilometer. So it's so Earth is 10,000 kilometers roughly in size. So it's probably 7 here. Yeah, so this is Earth is here, and you see it's far away. Okay, a chocolate bar It's considerably smaller than a person or Eduardo. Yeah, and it's going down now. Very good. And there is a known object here. Wow. Virus, very good. So we have something very small. So it's 10 to the power minus 20 kilograms. And it is of size, so minus 10, it means slightly bigger than an atom. And virus is like 100, or well, it's maybe 1,000 atoms together in size, roughly. Very good. We can, and something appearing here, ooh, we even cannot see it. And the moon, so moon, well, maybe some mistake in how we want. Oh, so it's a mountain. This was a mountain. Okay, I wait for 2 more entries and then we proceed. So you see, most people, when they ask to choose an object, they will choose something which is compatible themselves. It will be a person, so laptop, phone, chocolate bar. So all these objects are roughly of the same size compared to the size of the Earth, the size of the virus. Well, moon is unlikely to be here, but it's also something different. So I know that this exercise takes some time, so I did the homework, and we'll go to my homework preparation for this exercise. Yes. So, all right. Mm-hmm. Does it work? Very good. Very good. So I did my homework and prepared quite a few entries in this plot. So let me repeat what we are doing. On the horizontal axis, this line here, we are plotting a logarithm on base 10 of length of the system. So here we have 10, 20, 30. It means 1 with 10 zeros, meters. So it's 10 billion kilometers, 10 billion meters. And this is minus 10. It's 0.0090 and then 1. So this is 1 angstrom. And so, for instance, size of radius of the hydrogen atom is 0.5 angstrom, a little bit smaller than this point here. But also we have objects which are much smaller than hydrogen atom and even smaller. Well, at the moment, these objects, well, we say we could have these objects in principle. However, I tried hard, and for some reasons, which we are going to discuss now, all the objects I could invent actually never went to that small size. But I tried really hard and I found quite a bit of objects. So let us explore this plot in detail. The names are very small, but when we go little by little, you will see how they are organized. All the things that we suggested actually belong to only one class of objects, which is called chemical matter. These are the objects that consist from molecules or from atoms and not something more exotic. What I want to tell you today is that all the objects in the universe eventually have their size and size and weight as a result of balance between usually two, sometimes three effects. In particular, chemical matter is a balance between only two things. One thing is Coulomb energy or Coulomb force of attraction between proton and electron. And so this is a charge of electron square because proton has the same charge as electron. And R is distance between proton and electron. This is just Coulomb energy of electrostatics. There is some coefficients, but for what discussed today, the coefficients is not important. We make it very rough estimations of different forces in the nature. On the other hand, we want to compensate potential energy of electron, which is Coulomb energy, with this kinetic energy. So electron class in classical world would spin around like Earth spinning around the sun. So it's not exactly a correct picture, but still average kinetic energy of electron will be indeed equal with some coefficients to its potential energy. This is called Virel theorem. And this is balance between potential energy and kinetic energy, but all this is about electrostatics. What we have to enter is a second principle in nature, and in this case, it's quantum principle, is Heisenberg uncertainty principle. Heisenberg uncertainty principle says that we cannot know for sure momentum of electron and its size. Suppose we want to take electron and shrink it to the atom, to the proton, so it just falls down. If it falls completely down, then its size, its distance will be very small, hence we know very precisely its position. But by Heisenberg uncertainty principle, if position of electron, which will be roughly distance to the nucleus, is very small, P, which is momentum of electron, should be very big because it's Planck constant. It should be bigger than Planck constant divided by position, uncertainty position. So if electron falls down, its momentum on average will be very big, and hence its kinetic energy will be big. And then you cannot balance between two things. So in reality, you shrink electron onto proton only until the moment kinetic energy of the electron, which is originates from Heisenberg uncertainty principle, balances electrostatic attraction. So what in practice we do, we just substitute P with h bar divided by R. And this will be easy equation on R, which is solved by this formula. And this will be what is called Bohr radius. This is the size of an atom. We describe electrons more precisely not as orbiting around nucleus, but by wave functions. Size of this wave functions of roughly 1 angstrom. And on this plot of chemical matter, hydrogen is here. In this case, actually, it's H2, but it doesn't change much. So indeed, you see it's 10 to the power minus 10 in this direction. It's very small size. And here it's corresponding mass. In this case, it will be mass of a proton. Proton is two times heavier than electron. So it determines fully the mass of your system. And now, the moment I establish the size of a simple atom, size of all other atoms, there are 100 more atoms roughly in the universe, in the periodic table. They're roughly the same size, a little bit bigger, maybe a factor of 10 maximum. It will be, this is why this line is a little bit wide. We actually, what we do next, we take these atoms and densely pack with them all the matter. It's not like absolutely dense, but distance between atoms is not really significant, and it's very close to dense packing. And when we make dense packing, we get all the possible chemical matter. So on this plot, we have coronavirus, bacteria, nucleus of a cell with DNA inside. Fat cells can be very big. Then I have a laptop here, human. This is blue whale, it's just big animal. And now it's becoming very interesting. So this is Halley's comet. It's still on the same planet. We already came to astronomical objects. It's not just human-sized objects, much bigger. Here we have Sirius, dwarf planet in our solar system, a little bit bigger than Sirius's moon, orbiting the Earth. And here actually all the planets. So the last point is Jupiter. So you see that actually chemical matter, it starts from simple atom and finishes with the biggest planet. And all of them lie on this simple curve, which is just a linear curve. Logarithm of a mass is equal to 3 times logarithm of size plus some number. Why 3? Because size to the power of 3 is a volume. So it's basically saying that cold chemical matter roughly has the same density. That's it. And in reality, it changes between 1 gram per centimeter cube to 20 grams per centimeter cube by factor of 10, maybe 20. There's this difference between you take light element like lithium and heavy element like iron, or maybe even more heavy, even something like platinum. You get maximum factor of 20 in reality between things. So factor of 20 on the scale of the whole universe is nothing, and you really perceive this as nice one line, all the chemical matter fits. And all this is just balance between electric force and Heisenberg uncertainty principle, nothing else. Now we depart from chemical matter and discuss some other type of matter. Next on my chart is stars. In the case of stars, new things come into the game. It is gravitational energy. Even for planets already gravitated. They form themselves shape of a ball, but still their density is roughly the density of normal chemical matter. Things changes when we speak about stars. When you have gravitational energy of a star, in the core of the star, gravitational energy becomes stronger than electric repulsion, and between two protons, and what can happen, you can start having fusion. Fusion starts, it's a very energetic process, and because it's a very energetic process, a lot of energy is expelled, and this energy expelled actually pushes stars outwards. For the case of the stars, there is no simple relation between size and mass. There are different kinds of stars which I'm going to explain today. So instead of drawing nice curves, I just showed you some region where stars live. Star can be as small, but by the way, if you just ask when this happens, it happens when the mass of the object is 10 times smaller than the mass of the sun, just by simple analysis of dimensions. And indeed, the lightest stars that exist that can sustain fusion are 10 times less than the mass of the sun, and very heavy stars can be like something like 100 times mass of the sun. So this is a group of stars. Here, I cannot really say the law of mass versus size, but I can do it again if I consider white dwarfs. White dwarfs is another interesting object. It's not a star in the sense that it doesn't support fusion any longer. That's what happens with some stars after they die, after fusion stops. In this case, fusion cannot withstand gravitational pressure. Gravity pushes matter inside, it becomes denser and denser. And what happened next, we have to compare kinetic energy of electrons again, but this time not against Coulomb energy, but against potential energy associated with gravity. In this case, we have gravity of the stars times mass of star times mass of single electron. Here you have to play slightly more clever again, because you need to relate size of one size occupied by one electron, which is small r, to size occupied by the whole star, which is r. And their volumes is proportional with number of atoms inside the star. And number of atoms is mass of the star divided by mass of a proton, because all the mass is associated with the proton. Or neutron is roughly the same thing. So if you do your computation, then what you will get, then you will have this small curve here. And actually, I just put it here because it's very small. So just to zoom it out. So now you again have a very nice line. But in this case, it is very interesting. The smaller your star is, the more massive it becomes. Or it's actually the opposite if you wish. The more massive the star, the more it shrinks. Until electrons can resist. So this is here, this is what is called electron degeneration pressure. It's resistance of electrons against gravitational collapse because of Heisenberg uncertainty principle. Because electrons do not, if you smash them in very small volume, their kinetic energy becomes very large. So in the case stars become very massive, they overcome what is called Chandrasekhar limit. They become stronger than electron resistance, and they actually can collapse electron to protons and form neutrons. And the next objects we are going to resist star collapses are neutrons. And here we have another object here, which is called neutron stars. So this is blue dot is one of the pulsars in real. By the way, this is image of a pulsar. It's actually this is very small thing, but it's much heavier than a nearby star. It pulls matter on itself. And when matter goes very close to the star, it has very nice radiation that we can see and observe. So it's a very bright object because of this radiation. So a neutron star is balanced between now neutron kinetic energy due to Heisenberg uncertainty principle is called neutron regeneration pressure and gravitational pull of the object. So these are stars. There are stars, dead stars, which electrons against gravity, and also another dead star, which is neutron star, and a neutron star against gravity. Now we go to even bigger objects. Bigger than stars are galaxies, clusters, and webs. It's the three biggest structures you have in the sky. The next thing will be universe itself. And here, this is Milky Way. This is this Virgo supercluster. So all these dots are actually galaxies, and somewhere here inside is Milky Way galaxy. It's just one point. And this is what is called cosmic web. So this is like these lines actually formed by clusters. So this is the biggest structure. You have the universe, the next thing is universe itself. And here, well, I will not speak much about this. The only thing I want to say is that to explain behavior of this object, we need something very mysterious, dark matter. Nobody knows what is dark matter. The only thing we know is that it should be there to explain all the properties of galaxies, clusters, and webs. So what you say is that actually these webs, these lines formed as attracted by condensation of dark matter there. And now when all the clusters, these webs combine together, we reach the whole universe. And this is this point here. This is the whole universe. What is the size? Question to you, what is the size of the universe? What? Now. What is the size of observable universe? Hmm? 6 billions. No. So everyone watch Big Bang Theory, right? So they have this at the beginning of the first line. They say 13.6 billion years ago, the universe started from the Big Bang. So the oldest light is roughly 13 billion years old. And so you might think that actually universe 13 billion light years, but actually no, because the moment it was emitted and it reached us, the universe had 13 billion years to expand. So actual size is 80 or 90. It's from one side to another side that we can observe. It's between 80 and 90 billion years. So it's bigger than the lifespan of the universe because it's expanded while light was traveling to us. So this is something like 80 or 90 billion light years, and this is a mass. And now this point actually hits an interesting line. Who knows what is this line? It will be the next slide. To have an idea about this yellow line. No. The black holes, yeah, it's a black hole, it's a line of black holes. So it's actually very curious that I will come in a moment to this, why the universe hits in black hole. Yeah, so the next slide, the next type of matter is black holes. Well, not matter, okay, let's say it this way, massive thing. So in black hole, there is natural size, which is its radius, it's called Schwarzschild radius. And again, it's balance, which is between two things, or rather when this balance was broken, then it became a black hole. And then it's actually self-restores all the time. So in this case, we balance gravitational energy of our very massive objects against Einstein energy, energy at rest. So if all the mass contained, so suppose we have some mass which has that amount of energy at rest, and suppose this mass is confined inside a radius which is given by this formula. So it's very dense in a sense object. So all the mass are confined inside certain radius which can be solved from this, found from this equation. Then actually all matter collapses disappears and goes to space-time geometry, which is geometry of a black hole. So what happens if star shrinks? First, its electrons will stop. If it's still more massive, then neutrons stop it. If neutrons cannot stop it, then at least people will. I will tell you a little bit more, but there is no good candidate after that. It shrinks to smaller than this radius. It has a name Schwarzschild radius, and then it's actually matter transforms into space-time geometry of a black hole. So Einstein formula tells that we can transform mass into different types of energy. In this case, it will be energy contained within a black hole. So this line here is a line of black hole, of possible black holes. In this case, radius is proportional to mass. For normal matter, mass is proportional to cube of a radius, r to the power 3, because r to the power 3 is normal volume of space. Yes. Mass normally proportional to volume occupied by the object. In the case of black hole, mass of black hole proportional to just its linear size. And this line, so if this slope was 3, this number is 3 here, this slope is 1. And you see, so here is sun, the sun is here. The fate of sun after it dies will become a white dwarf. If star is a little bit more massive, it can become a neutron star. And if it's slightly more massive, it's actually, neutron sun is very close to this red line. If you zoom it in, it's slightly not reaching it, but it's very close already. And just a little bit more and it hits, and this will be a black hole. So I actually found some black holes on the market. The most important for us is called Sagittarius. It's a black hole inside of, in the middle of Milky Way galaxy. And by preparing this lecture, I was surprised to notice that observable universe also very close to this black hole bound. And actually, this is a little bit counterintuitive because you see, oh, yeah, kind of, it's not that dense. You think that black hole is super dense object. Well, it's super dense object when you speak about masses of size of the sun. So if this is sun, this is black hole. It's clearly the same mass, but much less volume. So it's much denser than the sun. So if you look down, it's actually black hole with mass of the sun is smaller in size than Sirius. It's quite small thing flying in the sky. So it's very dense. But you see that actually when mass of black hole increases, it's very relaxed growing in size. Not as a times 3, but times 1. So this is this line. And basically not very dense matter, eventually if it's normal matter, which proportional to cube of the size, actually will eventually intersect. And in reality, it should not be dense thing. It's just have to be big thing. And the universe is not that dense compared to the stars. I mean, this clearly, this thing is much to the right, so it's much less dense. But it eventually reaches size of black hole. So I will not claim that we inside a black hole or something like this is beyond my comprehension. But I'm just saying that just numerically, we at the boundary of Schwarzschild radius. of observable universe, which is, I found it's very amusing as a fact. Okay, your bet, what will be the next type of matter? We are not finished with types of matter. Yeah, now we go to the bottom, correct. So we exploded galactic sizes, cosmological scales. Now we go down. Next thing will be baryonic matter. It's when we strip away all the electrons and end up with only nucleus. Nucleus of on an atom consists of baryons, neutron and proton. And actually, all their particles of particle physics is basically this point. It's slightly different, but on these big scales, you cannot really distinguish them. So I tried 3 of them, then stopped because it was kind of pointless, just was 1 point. By baryons, actually, it's here also not only baryons, but also pions, mesons. So baryons consist of 3 quarks. Mesons consist of 2 quarks. They're all roughly the same size and mass. And also, well, I will come to this in a moment. Let me actually notice something. So elementary particles, electron, proton, or electrons, quarks, gluons, this is something that do not have size. Okay. For elementary particles, notion of size is very, very vague. But when you have a proton, which is composed particle, meaning of notion of sizes is very concrete. So proton has 3 quarks. Yeah, for 3 different color, if you wish. So there are 3 different points in space. And of course, you can draw a triangle which has clear size. So composite particles do have size. You can define it with certain uncertainty, of course, but it's reasonable definition. Whereas elementary particles do not have concrete size associated with it. They have something else. And this something else is called Compton wavelengths. Compton wavelengths is yet another balance. And now it's balance between Heisenberg uncertainty principle and Einstein energy. So again, so full formula for Einstein energy is the following. If particle moves, then energy is Pythagorean theorem of rest energy plus energy associated with movement. And if momentum is very high, we're interested in the situation when this part of energy, this here part energy, becomes of order of Einstein rest energy. If this happens, then actually we have enough energy to create another particles. So suppose we want to, again, suppose we have some object and want to shrink it to very small size. Just like we work hard to shrink it and shrink it and shrink it, become smaller and smaller and smaller. Because it becomes smaller, we use Heisenberg uncertainty principle, saying that its momentum becomes bigger and bigger and bigger. If it's, and the moment it becomes very big, its energy becomes so big that it can create new particles of the same type. So attempt to force particle to very, very small size, it's much smaller than size of an atom. It's the next level of smallness. Will end up with creation more particles. So you will fail to shrink it because you will just create more particles, not shrink the object. This limit is balance between Heisenberg uncertainty principle and Einstein energy. It's called Compton bound. So you just make this to this equality and Heisenberg uncertainty and compute. In this case, size and mass are inverse proportional. For black holes, they are proportional, and here they're inverse proportional, so it's sloped negative direction. So basically, you cannot confine, I mean, even if the object has no size, you can ask where it's confined. You cannot confine an object in a size smaller than its Compton wavelengths. Then you just create more objects of the same type. So in this sense, if you ask what is the size of electron or whatever elementary particle, it doesn't have size, but it's reasonable to assign Compton wavelengths. So it's because it's the smallest size to which it can be confined. And it happens so, this is quite non-trivial, that actually even composed particles are coming very close to Compton bound as well. So in this diagram, we cannot even distinguish them. So for composed particles, balance between strong interactions between gluonic forces. But nevertheless, they come very, very close to Compton bound. So I just can roughly say this is also satisfied. So this is a proton. This here is actually, I just was curious. This is Uranus. It's a nucleus of Uranus. And it's again running on line on the perfect slope 3 curve, the same as this one, just shifted. It has high density. And the most amazing thing is when we go all the way here, we crossed it at neutron star. So neutron star has exactly the same density as the nucleus. This means that it's just a very, very big nucleus. It's just densely packed with neutrons. That's what I will call baryonic matter. It's actually not only baryonic, it's all particles, elementary particles have roughly the same energy. Baryons and also mesons. Okay, now we learned about 2 important bounds, black hole bound on top and Compton bound on bottom. We can never exceed them. And so now, finally, we come to the point of this lecture, which is when these 2 bounds do intersect the point, which is very, very small size, 10 to the power minus 35 meters. And this is called Planck scale. So black hole bound and Compton bound meet. This is how small the size is. And this is the smallest conceivable size you can imagine. And we believe that at this size, something happens with everything, including space-time. This, by the way, doesn't have that small, its energy is quite big, actually. It's 10 to the power minus 8. So what is this one? It's actually bigger than its mass is bigger than the mass of a cell, for instance. Planck mass is quite big, actually. It's very small in size, but it's, of course, very dense thing, and its mass is quite big. So Planck scale is the ultimate goal. Notice that black hole size is combination of gravitational constant and speed of light and mass of object. Compton wavelength, L, is combination of Planck constant and speed of light. And Planck scale combination of 3 fundamental constants: Planck constant, gravitational constant, and speed of light. And the same here, different combination of the same 3 fundamental constants defined for you Planck mass. And we notice that there are 3 fundamental constants, H, G, and C. And here we come to actually the motivation behind these lectures, which is called cube of theoretical physics. So we have 3 fundamental constants, which is Planck constant, speed of light, and gravitational constant. When we ignore all 3 of them, this is called Galilean mechanics. This is the one we are used to. This is where we have our chocolate bars, which we eat. This is Galilean mechanics. Well, chocolate bars can fall. It's a minor thing, really. Now we can choose to consider a situation when one of the constants becomes important. So the first lecture that we are discussing was quantum mechanics, and we said that the Planck constant is important. So we consider things whose what is called action, is momentum times coordinate, is small enough that Planck constant is important. This is quantum mechanics. We had another lecture when we considered speed of light is important, when we go very fast. So what is, we go in the red car and how we look in the red car? Shorter, but not nice. You use some nice word. You look stupid, right? I mean, when you go on a red car and short because of Lorentz contraction, you use stupid. That's why I do not want to go. Right. So if speed of light is only important, we get special relativity, and the gravitational constant is important, and only gravitational constant is important. This is normal Newton gravity. It's about falling apples. And general relativity that we discussed here was actually a combination of G and C. We also had lecture on quantum field theory when this was fast objects and also small. And in this story, we had 2 more points. Is this point when everything except C and all together. So this point is kind of funny one. If we think about influence of gravity on quantum system in one direction, then it's perfectly fine. It's just normal quantum mechanics. By the way, there were experiments that confirm this. So particle in the gravitational field, you solve Schrodinger equation, and you get answers that were verified on experiment. This was done. Interesting part about this story is that in normal Newton equation, you have always a ratio of inertial mass and gravitational mass. They always have a ratio which cancel. If you want to write Schrodinger equation, they will be not in a ratio. They have two masses which actually not in a ratio. They're equal, but it's more funny how they equal. Well, it is less trivial. So there is no obvious equivalence principles there. Nevertheless, if gravity acts on a quantum system only, the experiment showed there is no problem. It works. Problem starts when quantum system acts on gravity. Then gravity should be quantum. And actually, in this case, we automatically, most likely, it will be such energy that we live to this realm when all three constants are important. And this is what is called quantum gravity, and nobody knows what it is anyway. What I'm going to do today, I will spend just a little bit of time telling you a little bit about what people try. Most of the time, we will not even reach that point. And this is a wholly direction from many theoretical physicists, and this also was organization behind this lectures in reality. And yeah, in the final poster for this lectures, this cube of theoretical physics exists. It has also one more direction. In this case, the Boltzmann constant, or let's say number of particles, if you wish. It's a statistical direction when you have many number of particles. And it's surprising that this direction is also very important, even when we want to study quantum gravity. This is yet another amazing thing about studying quantum gravity, that number of particles somehow helps. Okay. So let us summarize. And then I think it's even good time to go to the break. So we discussed scales in nature, and we discussed that there is the standard thing which we have in our mind is dense chemical. Dense is a thing that's not like gas, it's solid or liquid. We have chemical matter, which start from hydrogen and as other atoms, and go all to the Jupiter, which is almost at the star region already. Then we have stars, which have, because fusion is kind of hard to predict. And after star dies, we have white dwarfs, neutron stars. And neutron stars is actually the boundary of baryonic matter. So baryonic matter is all this line, but in reality, in the middle, there is nothing. It's either a nucleus here, well, up to something like 300 baryons in the nucleus, or it's already star. In the middle, there is actually nothing. There is also this cosmological size of things, and important thing that you cannot be bigger in mass than a black hole bound. It's actually funny because it's also Bekenstein-Hawking bound. So it's a black hole and Bekenstein-Hawking was nice to write BH. And you cannot be smaller in mass than Compton bound. Two bounds meet as Planck scale, and this is where we are going to go after the break. Okay.
So you were showing this cube of theories, and I was wondering whether at the angle where gravity and quantum physics are important, but special relativity is not there yet, would you say that white dwarfs are sitting at that point? Other white dwarfs sitting in that angle of the cube? Yeah. So,
I mean, for white dwarfs, quantum gravity is not important.
But quantum mechanics is kind of important.
I think it's basically this corner is. I think in white dwarfs, the quantum gravity is for nothing in there. I mean, you just do classical gravity with them, and you're perfectly fine. So this would be my answer. So yes, the white dwarfs is basically here. You have your electrons in the potential of gravitational field, which is fully classical. You do not need to quantize it. Yeah.
About the Schrödinger-Newton equations, again, that corner of the cube. You mentioned there are some experiments that can confirm.
Yes.
You know which kind of experiment?
Yeah, I forgot the name. I can show you. Do I have it here with me?
Okay.
Yeah. Okay. There's a name here.
So like experiments in lab or in the
solar
system?
Okay. No, it's honest experiments that people conducted. Yeah, so I can show you here, just here in this paper.
Okay. You didn't know. Thank you.
Yeah.
If I can comment something. So you mentioned that black holes have size, but elementary particles don't have size. I think actually talking about size of the black hole is a little bit fishy. So like Schwarzschild radius is a scale which you can associate with the black hole.
Yes.
In the same way, Compton length is a scale which you can associate with elementary particles. So in this way, black holes are actually much closer to elementary particles.
Very
so
good.
They have the same feature of not having really size defined.
Indeed. So black hole doesn't have size in this sense. It has some important scale. And likewise, elementary particle, yes, so indeed. Yeah. Yeah. Yeah, so 10 minutes past 7, we come back. Yeah.
Okay, yeah, let's have a break till 10 past 7.
So let's continue. So in reality, what we have here, we have two bounds and also this line of baryonic matter. And inside we have a triangle which is in principle very badly explored or almost non-explored by humanity. And this would be like push forward to know for physics in future. Of course, eventually we want to reach this point, but in reality, you also have to understand everything before. And we can think about three things to do. Going by green line here, by red line here, or somehow jump like ad hoc directly to the Planck scale. So I will do first green line. And the green line is actually what is done on all accelerator physics, like the biggest Large Hadron Collider, LHC, and it's actually covers this type of scales, this type of distances. So it goes beyond the baryonic matter, but well, reasonably actually good beyond, but still very far away from what we want for Planck scale. I will slightly explain what is being done there. We did it last time, but today we'll make some other emphasis on things. So small recap about particle physics. There is very simple result behind all the particle physics. You have to apply quantum principle and on top of this symmetry. Last time we discussed already some symmetries, and important was global symmetry. Before we have gravity, it's global. After we have gravity, it's a different story. Global symmetry has translation in space. So if you translate in space, then particle has momentum. When there is a change in time with symmetry, it has energy. Then boosts change of reference frame with velocity. Say that there should be some constant which is called mass. And finally, rotation in space give a particle a spin. And standard model particles have fermions, spin 1/2. It's so pink are quarks. These are heavy fermions, and green are leptons. This is electron and neutrinos, and there are 3 generations. This is fermion spin 1/2. They make matter. Spin 1 is interacting fields. And also now humanity discovered spin 0, which is Higgs boson. For this table, we have to add today 2 more things, which is spin equal to 2, which is a graviton. And it will take its role in the game. And there is in principle missing piece spin equals 3/2. Well, there is no candidate which is also observed for elementary particle with the spin. My goal is to explain a little bit why the spins are important and why this particle is bounded by spin equal to 1, and what we have probably later. So for this, I need to recall what is quantum principle. Quantum principle is that you do not get exact answers. You should compute only probability, and probability is to get probability of something. You have to sum over all possible scenario which can happen in the whole world. So you have to sum up with certain numbers in front of, and if you do this, you hopefully get your correct probability. This is what is quantum principle. But of course, number of possibilities to sum over is huge, like infinity. Usually it's infinity ways to do something. And when you have infinities, you have, of course, problems. You know, there are many paradoxes related to infinities, and these paradoxes are very real in quantum world. In fact, the very first infinity problem was overcame the moment quantum mechanics was born. It was happened in the beginning of 20th century, 1900, when Planck derived formula for thermal radiation. And his formula resolves a problem which is called ultraviolet catastrophe. This is first example of infinity ever like seriously affecting physics. So what is the problem? I give only this very explicitly, then it will be much less explicit. When you look at fire, well, especially this part of it, big part of it is thermal radiation. It radiates light at all possible frequencies and directions, just because molecules inside are very hot, they move a lot. And because all possibilities happening, this is not quantum mechanics, yes, it's statistical physics. We want to compute average energy of radiation, and recipe is very similar to quantum mechanics, just the numbers are different. You have to sum over all possible ways to emit light with certain numbers. And if you do classical light has some energy. Energy is related to how high this oscillation, or this yellow oscillation. They are the same. So you can have arbitrary energy, but also light has a direction, right? So light can look at any direction in sky. So these are your parameters. You have to sum all over. Direction is encoded into a vector. Oh, it's here k. So I just wrote for you. Light is emitted from this point, has some direction. Length of this vector is dictated by wavelengths of the light. So lambda is wavelengths of the light. And now you ask yourself a question, okay, what is energy associated to light emitted with certain frequency? Let's say, okay, this is kind of yellowish. So what is energy associated to yellow light? And because you have to sum over all possibilities, and clearly any direction has the same weight, you end up with summing, computing surface area of a sphere, because here it's all possible direction when light can be emitted. And surface area of a sphere proportional to k squared, just surface area of a sphere formula. 4 pi. 4 pi. It's slightly wrong, but okay. And because k is 1 over lambda, what you see here, that this energy becomes infinite when wavelength goes to 0. This is what is ultraviolet catastrophe. Classical physics predicts that very short wavelengths, immense amount of energy should be emitted at very short wavelengths. And well, this of course cannot happen in reality. This is a catastrophe for classical prediction. And so lambda small, wavelength small is ultraviolet. And what happens actually at very small distances, something wrong happens with our theory. Well, we know what happens wrong with our theory, small distances should be quantum. And in the case of light, actually, all distances should be quantum. But for small distances, it's important to get the correct predictions. And how it resolved that energy cannot be arbitrary. Classically, this fluctuation can be big or small, whatever. But in quantum world, the energy of the light should be proportional with integer number to Planck energy, h omega. And because energy cannot be arbitrary, you cannot excite a very small short length with arbitrarily small energy. You should pay a tax to excite very short wavelengths, and this saves you. Because this tax becomes very high when the size of the wave is very short. And this how problem was resolved. This first example of quantization, resolving infinity problem. And it leads to Planck formula for black-body radiation. For you, it might look horrible, but believe me, it's one of the most beautiful formulas ever exist in theoretical physics. And we can spend the whole lecture just explaining why it's beautiful. I'm not going to do this now. So after some time you do theoretical physics, I do a lot of formulas, you know, that is beautiful actually, for many reasons. And for instance, example of thermal body is the sun, our sun. Our sun emits the thermal radiation at around 5,000 Kelvin. And this is its emission spectrum. Of course, it's not exactly right because there are a lot of things happening on the crust of the sun and on the way to Earth. But you see, it's kind of this yellow thing is what the sunlight spectrum looks when it approaches Earth. It's very close to black-body radiation. And when it passes through atmosphere, there is absorption lines because there is water atmosphere, oxygen, so it gets distorted. But now you understand why it's distorted. Interesting part that the maximum of this radiation is visible light. And now you should be amazed to say, yeah, sure. So why do we see at visible light? Well, because sun emits light at most at this wavelengths, and of course you have to adapt it to most favorable conditions. I presume if you live near some other sun, which have somehow shifted maximum of emission, you will also see living on a different planet, a different place. However, this temperature is quite typical for stars around which it's good to support life. Another example of black-body radiation, thermal radiation, is cosmic microwave background, which we come to this very soon. So this is this famous picture which we see in the sky, which make us swarm. Right. So this resolves one infinity, but in quantum field theory there are many more infinities. And I will not go into the details, but I need to say few things just about them. So the point that this is what we discussed last time in quantum field theory. So we have electron emitting photon, interacting with other electrons. And because there's some overall possible possibilities, for instance, this can happen on this stuff. Another photon emitted, which creates electron and positron pair, collapse, and so on. So the number of possibilities here is also infinite, and they actually produce actual infinities, which have to be dealt with. And this is why it's quantum field theory is hard. We need to know only two concepts today. First is full gauge symmetry. So there are two classes of infinities, important and bogus. Bogus is just because you had very bad description. Very bad description coming if you don't count gauge symmetry properly. So what is gauge symmetry? Remember the story that in quantum mechanics, we have a clock, or actually a complex number, which changes when we move through different trajectories. This was like I showed almost every time I give lectures here. If you remember special relativity and gravity lectures, you know that there is a problem of synchronization of clocks. So in reality, before we even start doing this picture, we have to assign statement what is the same direction of clock at every position in space. But notice this is not clock measuring time. It is actually some complex number. We have to agree between ourselves what is the same complex number at different points of space. It's exactly like in gravity. In gravity, we have to agree what is the same time at every point of space. It's a big problem in gravity. And here we have to agree how to assign the same complex number at each point of space. And ambiguity in assigning these numbers is called gauge symmetry. And actually, these are photons or fields associated to electromagnetic interactions that controlling how complex number at different points are synchronized, if you wish. So photon tells if you move from this point to this point, how should we rotate this number? This is quite interesting. So this is called scientifically U1 gauge symmetry, and it is electromagnetic force. In quantum field theory, something interesting happens because it appears that we also need to consider not only one complex number, but two of them, like this. Then behind this gauge symmetry is weak interaction, and if there are three numbers, then it will be strong interaction. And for three numbers, I can appeal to computer graphics. So for instance, you're making a game, and you have to move the object around, right? So you play some game on computer. How do you do this? So what you can say is that every point is collection of three numbers, and you have to transform these numbers to move it around. And transformation of these numbers is multiplication by a matrix. So if somebody did computer graphics, knows it. If not, okay, well, that's what you do. And so this is kind of the same thing story here. We have three numbers. It's almost like the same as the point here, except this is a complex point. And this matrix here, which is 9 numbers, is 1% actually only 8. This is a matrix actually giving you gluons. So we have these three interesting symmetries corresponding to three interactions inside the nucleus. In total, so in principle, depending on particle, we can have only one of them or all of them, then it will be actually 6 complex numbers in total. So why I need it? Because I wanted to tell you something funny. So quarks, do they repel or attract? Well, the interesting point that I will skip this, but the interesting point that if you have quark and anti-quark, they attracting. Quark, anti-quarks are always attracting, and this is normal because they should form a meson. Meson is always composition of quark and anti-quark. And by just changing sign of charge, you can see that quark with quark actually do repel. But if quark with quark repel, we cannot make proton. And here comes importance of having these 3 complex numbers, because when you have 3 complex numbers, you can make a very new special interaction between 3 quarks, and 3 quarks actually do attract. So 3 quarks together attract, whereas 2 quarks repel. So it's like some balance again between attraction of 3 quarks together versus repelling of pairs of quarks, which creates for you your baryon, neutron, proton, or something else. And but of course, it's just a 3-level approximation. Serious computation is done on lattice QCD. So you have 3 quarks and these gluonic tubes in between that actually control strength of interactions. This will be more precise. And this is meson. Blue is quark and red is anti-quark. Okay. So gauge symmetry, if you treat it correctly, it removes these bogus infinities. Now about more serious infinities. There are other infinities much more serious, and they're happening because at very small scales, our theory is just wrong. We have no idea how to change it, so what we do, we could cut it out, very high energies, and we try to replace it with some effective description. So what we do is we replace this interaction with some effective interaction. And this effective interaction is just a number which takes into account effects from all the high energy, very small distance sizes. We do not know what these effects, but we hope that by this only one number, we can somehow account for all of them. This is called renormalisation procedure. And there is a very nice example of renormalization, the American elections. So you know how American election works? So at every state, people elect not a president, they elect voters who then vote for president. So this example of renormalization procedure. So if a majority of people voted for Donald Trump, then all the voters in this given state become red, and then they act effectively in name of all people. So what I'm trying to do here is something similar. We have complicated math, which we do not know how it looks like. It's even infinite, but we do not know. We don't want even to care. And we want to replace it only by one number. And this will be, our electors who will elect president. This is called effective couplings. The only thing we need to know about this when we introduce them, they depend on how much we throw away. So we can say, okay, starting from this size to everything smaller, we throw it away. Or maybe from this size, we throw away. And depending on how much we throw away, effective coupling will be different. Right? Well, because we change what we throw away. So it's normal that the answer should change. So what you have to keep in mind is that effective coupling depends on what energies or the same size of your system do you want to consider. If you want to small, it's one coupling. If it's big, it's another coupling. And here you have to remember about quarks repelling and attracting. Let's consider first electrodynamics, electric fields. Suppose we have an electric field propagating through space. In quantum mechanics, everything can happen. Simple thing that can happen, which is not simple to describe, but it can happen, is that quark and anti-quark is created. Quark and anti-quark act as dipole. So if it's plus charge here, minus charge here, they will rotate and slightly decrease amount of charge. So these are called vacuum pairs. And what they're doing, they are screening away charge. So to have electric charge of electron as it is now, at much higher scales, charge of electron should be bigger. Vacuum fluctuation, or what's called vacuum polarization, actually decreases strength of electric charge when we go to lower energies. So very high energies, electric charge is much higher because then at high energies, much less of these guys can happen. For chromodynamics, when we have gluons, there are two things can happen. They can be quarks. So electrons are replaced by quarks, and so they do the same job. They screen away this gluonic charge or strong coupling interaction. But this existence of three colors allows to create a new possibility, creation of gluons out of another gluons. And gluons actually do opposite. They do anti-screening. They actually increase your charge. So this means that because of gluons, your gluonic charge is bigger at small energies compared to large energies. So you need to have very small gluonic charge at large energies to have observable gluonic charge at our energies. And indeed, actually, when you compute everything, these two effects, the second effect wins. And we have two important effects. So here in electric dynamics, when you go to very high energies, your electric charge becomes super, super big. It's called Landau problem because you do not want super big charges. But in chromodynamics, it's the opposite. When you go to very, very high energies, your charge becomes very, very small. Almost no interaction happens. So quarks becoming free. And this is called asymptotic freedom. Then I will just very briefly show you spontaneous symmetry background. So can you help me with the experiment, please? So this is Higgs field at very high energy. Can you go from that side? Now, what we are going to do, okay, we are going to lower energy of the Higgs field. we are lowering energy of the Higgs field. Okay. So what was about this experiment is that we have rotational symmetry, and if Higgs have very high energy, it wants to be in the center. But despite rotational symmetry exists, when energy lowers, it actually wants to go to one of the sides, but going to one of the sides breaks symmetry. This is called spontaneous symmetry breakdown. I decided to not go into details today about this because you need to go to other stuff. But the point is this mechanism creates mass of all the matter that we have. So this is what recently we detected LHC is that Higgs exists and creates mass for all the stuff. Right, so as I said, I'll skip. Okay, and so now, after you learned about this particle physics, I can make some summary. So when you do LHC, you know that there are three forces. So blue is electromagnetic force. And when we, okay, right. So this is, sorry, I had to make mirror reflection. So this is 1 over coupling constant. So if it go down, it means charge becomes bigger and bigger. So electromagnetic force, when you go to higher energies, so this direction means smaller sizes, and by Heisenberg-Concerton principle, it means higher energies. So if you go in this direction, one green line increases, so you go to high energies. And so when you go to high energies, electric charge increases. So decreasing here means increase of electric charge, and charge associated to SU2, it's weak interaction, and SU3, strong interaction increases. So there is an interesting region when they intersect. It's called grand unification scale. When all the forces become of the same size, it's this called grand unification theory. It's somewhere here. So it's where we treat roughly the same all three series, all except gravity. And this happens between 10 to the power minus 27 in this region, minus 33. So it's very close to Planck scale. And we hope it will happen, but we do not have experiment to go there. It's just extrapolation. And there is this region here is called electroweak scale, 10 to the power minus 18 meters, where this spontaneous breakdown happens for Higgs. So basically, LHC come very close to it. It already can show Higgs, but what we want is just to climb a little bit more, because actually, there is an open question, which is kind of strange, but it exists. Why this number? So this number, remember at the very beginning of the talk, I told you that everything that happened in physics is the result of balance between two things. And if balance is broken, we come into new physics, from chemical matter to stars and so on. So this is a scale at which Higgs decided to go from the to the side in its roll to the side of its potential. It means that balance of something was disturbed, but we do not know what is this something. And if there is no new physics here at all, and the point is that we do not know any new physics there, then we do not have any reason to have balance to be destroyed. So the point that scientists hope that starting from here, which is very close to LHC capabilities, but not yet, we hope to find something new physics happen, because there should be something that destroys balance, making Higgs to get non-trivial expectation value. And this is what people want, and but yeah, just a little bit more budget. And then maybe. So this is hard because we already kind of at the limit of the budget, right? LHC is super big already, still 200 less than military budgets. But well, so it's now becoming a big political question. But we hope that new physics starts somewhere here. This, of course, unhappy scenario that new physics starts only here, and then it's hopeless. If it's then it's kind of means that we'll never be that rich to do experiment. Right. So this was particle physics story. So let's see, coming close, but not yet to what we want. And now let's go to gravity side. Okay, finally we're going to gravity side. So we go to this line and think what can happen in this direction. So first thing is actually notice that we have one more type of matter, which is actually reasonably confirmed by now. It's actually quark matter. It's when we're already asymptotically free reasonably. So it's reasonably weak interaction between quarks, and they are condensed. So like neutrons smashed in one big soup. So actually this is nice scientific phase transition diagram. So this is hadronic phase. Normal hadronic phase is the same as this baryonic matter, is the same thing. Neutron star core is what I told you before. And this quark gluon plasma, it's very high temperatures and some energies, and LHC actually here. It's in this quark plasma. So this is scientific picture, and this is a cartoonish picture of the same thing. So it's about up to 10 times denser than baryonic matter, and then in the core of neutron star we have it. And at LHC we have a heated version of it. So people reach this. Okay, let's skip this part. Then, okay, the story was to make it short. People try to find some exotic stars. So we say have stars consisted of neutrons. We have inside neutron stars quark core consisting of quarks. Okay, but what about maybe you have stars which make a fusion of electroweak scales? These stars were proposed in literature. And of course, because they should be below this black hole bound, they cannot be massive. So they cannot exist by themselves. So there should be like core instead of bigger massive thing. And well, scientists did not reach this proficiency. So for the moment, no exotic stars, of which would be some other type of matter, which will be very nice, of course, because we will explore this region, but it's not far. And also people did not observe any small black holes, only big black holes of size in the center of galaxies. Why black holes are possible to observe? Because they have Hawking radiation, and we're going to speak about it. But they were not observed. So basically, in this direction, gravity direction doesn't help, but then we probably can go actually somehow strange opposite direction. And here we have another trouble, which is called dark matter. Nobody knows what to do with it as well. So there's a big list of dark matter candidates. And cosmological scales at modern time are not promising to go here, but cosmological scales in the past are promising. So now, crash course in cosmology. So there is a model. The only thing you want to know, so what's the point? Einstein wrote equations of gravity, some equations. And he hoped that space is flat and never changes, but it's a gravitational object, just makes small correction to it. But what happens eventually is that massive objects inside space actually make space either shrink or expand. Space doesn't want to stay still. It's just a consequence of Einstein equations of motion. And the simplest is this model, Friedmann, Lemaitre, Robertson-Walker model. I explain what's here. A is size of the universe. Okay. This is density of different type of matter, whatever. It can be dark matter or something else. This is what is called cosmological constant. It's some parameter. And the point that it is typically non-zero. And a dot, it means speed of change of size, right? It's just normal speed. So the point that because this is typically non-zero, it means that size of universe will change. It can be positive change or negative change, but it will change. And more interesting thing is second derivative, acceleration. And here we have two contribution, negative contribution from all type of matter and so on, and positive contribution from cosmological constant. And modern days, this thing is actually already very small, and cosmological constant was shown to win. And universe today is accelerating. And we are here. So this is universe long time before. This time it expands, and now it's actually accelerated in the expansion. That's what's happening these days. Right. But if it expands, that means in the past it was smaller. And in this equation, it's very hard actually to achieve the situation when it stops changing in size. Actually, if it expands now, it's, well, we can compute that it was expanding in the past as well. So we can come back to the size and smaller, and eventually we come to a point which is Big Bang point from which universe expanded. So this is the idea of this cosmological model. And we can calculate back using mathematics what happens. And because we want to go to these very small things, that's why I will focus my story. So basically, okay. So from where should I start? So the point people computed expansion, backward expansion, and came back to the conclusion that it should shrink to a point, and before shrinking to a point, it should be of size of Planck scale. So this is basically singularity from where everything started. Then until this grand unification scale, honestly, we do not know what happens. But there is an important scale which is new. So notice why we are doing this discussion, because we're trying to make some hints of new physics. So cosmology predicts that there is something that is called inflation, and it happened when the universe was roughly of this size. And actually, we have to recalculate it in time. So it was 10 to the power minus 32 seconds, roughly. So what cosmology tells us that some amount of time, the universe suddenly expanded very, very fast. It's called inflation. And this is needed because otherwise very many predictions do not work. And this is set up a new scale, which is surprisingly between this electroweak scale and grand unification scale. So we hope for new physics again. And after inflation happens, actually people can compute everything. And they compute that first, even before inflations, Quark was already, so it's written here. So already quarks were separated from electroweak interactions. Then at some amount of time, universe was expanding, coming through this scale. This means that Higgs got a mass, and then protons formed. And then at some moment of time, we come to the time when atoms formed. 300,000 years after a Big Bang, atom form. And when this is called recombination epoch, the moment atoms form, radiation become free. And this picture of cosmic microwave background, which we had before, it's there long time before. Yeah, okay, good idea. Yeah, this one. This is the last, the first image we see from a universe. So the point that everything that happened before a recombination creation of atoms, we cannot see. Not using light. Maybe using dark matter detectors the days it will be created. But using light, we cannot see anything what happened before. So people have to, it's like an accelerator experiment. You know that in accelerators, we have a big collision of stuff, zillions of things happening. We measure gigabytes of data and have to reconstruct to find one Higgs particle. So it's kind of, Big Bang is like big accelerator experiment happened once. produces one big chunk of data, which is called cosmic microwave background, and people have to collect it and from it reconstruct what happened before. And that's what people are doing. They actually launching very precise experiments into space to find all the data is very precise, very high precision. So this is hope to get what happened. So basically what they want to use Big Bang as a super big accelerator machine to know something about physics. And for instance, we already understand from this picture, there should have been inflation, which is something new in physics to be explained. Okay, so this is what we can get from experiments. And finally, let us jump to the quantum gravity. So what I explained until now, that we tried accelerators, came here. We basically trace back a universe in time, and through cosmic microwave background, understood something about these processes here. We get some data, not everything. And this is the best we can do, and people still do working, and this is a very active part of research. But there is other part of people, theoreticians, who actually say, okay, we jump in and try to go to this point directly. We want to quantize gravity. So there are many theories of gravity that were proposed, and I will not list all of them. I just list some of them as a choice, the one which I hear most often with my ears. This is basically how a choice was done. Right, so first of all, why do we want to quantize gravity is, I told you about infinities. And I told you that we replace all the high energies with effective coupling. Can we do this? So the statement that we can do it for all the strong and weak and electromagnetic forces, then we can replace them with effective coupling, and this works. However, in the case of gravity, it's called non-renormalizable theory. If we just play the same game, we should introduce infinitely many effective couplings to take into account for all high energy corrections which we want to throw out. Of course, infinitely many couplings is not something we want. So so this approach will not work. We cannot use approach of effective couplings to describe quantum gravity. And instead, we have to come with completely new idea. And well, there are some new ideas. I will be very brief, just actually spend some time thinking how should I explain it. I did not find a solution. The only thing I can just say is this exists and give you some comments. Because it's like a second order intuition. I have to use intuition from quantum mechanics to explain this. But quantum mechanics has its own intuition, which is like not normal everyday life intuition. So it was really hard to understand how should I predict it. So the only thing I really can do is just name things and just give some idea. So first thing is called N=8 supergravity. This is something funny because I said that gravity cannot be described using these effective couplings. Well, everybody believes it cannot be, but actually let's do computation. And people created maximal 4-dimensional theory of gravity with as many symmetries as they could possibly do. You cannot put more there without having particles higher spins. This is really maximal symmetry you can do. And then surprises start appearing. So there are very many particles. So you see this like number of particles is quite big. 256, well, 1 byte of particles. But interesting part that people believe that the 3 loops should not be effective coupling will not work any longer. You have to do something else. But then people computed 3 loops and suddenly everything is fine. And people said, okay, 6 loops maybe 6 loops, okay, like much more complete computations, then we have troubles. And you know what? People until 5 loops proved that there are no problems. I mean, those who do theory know that 5 loops is incredibly hard. And there are actually examples that something at 8 loops is okay. So there is a chance that for some mystery, the theory actually has no troubles, and we actually should stop saying gravity is impossible as quantum theory. Maybe it's just okay. That's why it's interesting one. We do not need to invent anything here. We just pump as many symmetries as we can. And so far, we don't have a counterexample from this theory, or only positive things. For people who are doing symmetries, there's a beautiful story behind. So symmetry behind is exceptional Lie algebra, E7. And it's quite, it's actually, it's an extra bonus that people discovered. Nobody thought it will be there. And so it's kind of, you impose some symmetries, but even more symmetries pop up. So this is some mathematical curiosity. And this is first candidate because it's maybe just gravity itself is okay, but is with a big number of symmetries. So what is the problem? That in nature we do not observe all these 256 particles. We don't observe them. They should be broken by this Higgs story somehow. And we do not know how should it happen. Okay, example number 2, loop quantum gravity. I described with you the story that we have to tell how rotate objects when we move it in gauge series, and this rotation is encoded into interactive fields. In gravity, the same story, and this is what was discussed in gravity lectures. Actually, synchronizing clocks is done by what's called Levi-Civita connection. So there is a way to right. So in gauge perspective, we synchronize numbers at different points. In gravity perspective, we synchronize these points, but we always keep them tangent to our surface. So there is a way to decouple this smile from being tangent to a surface. We can move around without, so smile being tangent is one thing, but there is mathematical transformation which allows us to move it without stopping being tangent. So this is called tetrade formalism, or moving frame formalism. Basically, what we do, we consider gravity as a type of gauge theory in a sense. Then, in loop quantum gravity, they decided actually to slice in time. So time is important. Okay, we believe there is a symmetry. Okay, but let's destroy it and make time important. And then, well, here comes the most important part. Normal observables do not work. So the idea was to choose very cool observables, and they found that apparently not considering quantum fields, by considering loops over which fields should be integrated is a nice observable. And they actually change the game. Instead of computing these Fermat diagrams, they compute all possible. So what they're doing, they're drawing all possible lines on a three-dimensional plane with all possible bifurcation of lines. But then I apply quantum principles, the sum of all such possibilities. And this is what is called spin forms. So this is example of spin forms. So I start with some lines, then they evolve in time, and there are some rules behind. Well, what they did nice, they derived Bekenstein-Hawking entropy. Yeah, I will say a few words about this. Problem, they did so many cool things that they actually cannot reproduce normal world. This is a problem. But yeah, so it's one of the interesting things to do. By normal world, it means normal classical Lagrangian description. It's hard to reproduce. Okay, so string theory. Well, I will be very short. So two things. First of all, it's not like somebody sit down and said, okay, today we'll discover string theory. So strings appear from two things. First, there was some observation from accelerators about different Feynman diagrams. There should be some symmetries. And there is something, some relation between a spin of particle and its mass. And it was kind of guessingly that there are some mathematical expression which explain everything nicely. And this mathematical question came from this nice stringy object. And second thing, you remember this picture of quark intermediated by gluons. These gluons form like a string, and people was trying to write an action called number action to effectively describe the string. Well, they did it. Then everything came together, and they discovered that this description has gravity inside. And so people were very happy because this has gravity inside, and well, stereo gravity. What I wanted to say that they did not think down, okay, today we invent stereo gravity. They wanted to solve practical problems of life, and they end up with something which had gravity. This is how historic, and this is always in research like this. You always want to solve some practical problems, and somehow you get to some new discoveries. But okay, let me just tell you short about why strings. So the whole point in quantum physics theory is that when object is very small, you will have singularity. And you try hard, but you cannot solve the problem of singularity in gravity. So string theory says, okay, objects will never become small. At small distance, it becomes a circle. And circle is obviously not a point. And then there's no problem with singularity. So this is like very rough idea of string theory. Well, why people also like string theory? Because they impose niceness assumptions. And after they impose niceness assumptions, they found that only that many options exist, which is kind of small number of options. Well, drawback is 10-dimensional theory. You have to go to 10 dimensions to do quantum gravity. And not 4, but 10. And somehow then people also discovered that there are some dualities, which tells it's only one theory. So you kind of have only one theory in 10 dimensions, or maybe 11, because notion of dimension becomes blurred. Produce you gravity, produce you some field theory. So maybe that's it. Well, they still cannot reproduce real world. So it's quite, well, it's still hard computation. Right, but string theory get something different. It's like with the discovery of America. They wanted one thing, they got something else. So let me speak about black hole entropy. Right, so Bekenstein and Hawking discovered that black hole have entropy. And the logic is the following one. You want to design a system. You want to design a system which contains information, not mass, not energy, information as dense as possible. How densely can you pack information? Then you say, okay, the cheapest way to pack information is to use photons. It costs less, the least possible energies for photons. I want to have very low energetic photons because then it will be little energy cost for information. But low energetic photons is very long photon. Okay. So the cheapest thing you can do if you want to store information inside this box, wavelength of the photon should be as long as this box. You cannot make it less energy because if it will be less energy, it will be longer, so it will not fit. So associated with the length of this box is energy of a photon. Okay, and now how much photons can I fill inside this box with given energy? Well, as much as when I hit black hole bound, because the moment energy here exceeds mc square, photons will disintegrate, forming a black hole instead, right? And then you're lost. So all information you stored will be covered by black hole horizon, and everything you knew become black hole entropy. And this is the answer. Black hole entropy is this formula. It's Boltzmann constant, some area of black hole. So black hole is just a two-dimensional sphere in space. Well, Sasha, so it's not, well, horizon of black hole for two-dimensional sphere. It has area by normal formula 4 pi r squared, where r is this radius, Schwarzschild radius. So it's proportional to area, and there is Planck constant of Planck scale length here. And this is how much information you could have stored just before it became a black hole. this is basically how it becomes entropy of black hole, because after it becomes a black hole, entropy is lost. And now surprise came, because usually it's exactly like with matter. Amount of information usually proportional to volume of the system. But in this case, amount of information proportional to the area of surrounding blocks. And now we come back to this point. Our universe is very close to black hole bound. And by this Bekenstein argument, amount of information that we can store about our universe is precisely proportional to the boundary of universe. And this way comes the idea of holography, that we are actually a holographic image of something on the boundary, because our boundary is enough to store all the information. This is what Bekenstein-Hawking entropy tells us. This is the idea of holography, that we are just holographic images of something two-dimensional. Well, if this time is 2 + 1 dimensional, well, people tried to work, did not work very well, but instead they did something different. They changed geometry of space from flat to de Sitter to anti-de Sitter. It's just another geometry. And then they found that gravitational theory inside is indeed described by the boundary object theory, which doesn't have gravity. So they were able to exclude gravity from description of physics. Well, like not exclude, they can replace gravity inside, but non-gravity on the boundary. It's called idea safety duality. So gravity inside is black holes, all the stuff, completely crazy stuff inside is replaced by something without gravity on the boundary. And were they happy? You know what they're doing actually instead? They're not happy. They're using gravity to so on. They wanted to like solve gravity. Now they do the opposite. They say, okay, theory on the boundary is complicated. We are going to use gravity to solve theory on the gravity boundary. And this became concrete application. So notice, we wanted to quantize gravity, a lot of things. And now we came to the point that we actually get some concrete applications. For instance, they try to use this holographic principle to study superconductors and quantum critical points. So Sasha is working on it. He can tell you a lot. And also, it promoted techniques to solve some for exactly. So it probably mentions very hard math, but you don't mention how hard it is. But all these ideas inspired new techniques to solve four-dimensional series exactly. And just to tell you, this is where I'm working. And just to tell you that old-fashioned techniques allows to compute this quantity, whatever I don't know what it is, but it takes you 1 week to compute this quantity on a laptop. So using techniques inspired by this holography and all the stuff, it's enough 14 seconds now. So what happened, we developed completely new techniques to save 1 week of computation for something very complicated in field theory. And suddenly all this quest for quantum gravity became a concrete tool for almost, well, very close to real life. I would not say completely real life, it will be not honest, but we kind of came close to the questions which ask for real life. And we do not solve quantum gravity, but we found new computational techniques by trying to do this solution. So just saying that quantum gravity search gave you just new computational tools. You know that internet was discovered where people try to do also accelerators. Just another example. Okay, and finally, I just want to show you a cartoon. The last candidate of quantum gravity they will discuss is called causal dynamical triangulations. So triangle, so it's again computer graphics. You have a hair and you can triangulate it. This is, you can imagine, on computer standard thing to do when you make computer graphics. So this hair is covered with triangles. So triangles in mathematics called two-dimensional syntax. It's 3 points connected by edges. In 3 dimensions, it will be 4 points connected by edges, and this is tetrahedron. And in 4 dimensions, it will be 5 points all connected together. We live in 3 + 1 dimensional, so 4-dimensional world. And like this hair, this surface of this bunny is 2-dimensional, we can triangulate it. Our world is 4-dimensional, we can cover it with 4-dimensional simplices. And so there is an approach, it is based on a computer. We cover our world with simplices and describe very simple rules how they evolve with time. There's causality inside. There's not just, there's some direction here as well. And I will not, they can reproduce phases like, they can reproduce some phases of universe as we see them in reality. But let me just show a cartoon. This is 2-dimensional version of it. So this is our discretized space-time in this approach. 2-dimensional space. 2-dimensional space and 1 more dimension is time. And this 2-dimensional space is going to evolve with time in the presence of certain scalar field, whatever it is. Evolution of space-time, of space in time. It's quantum fluctuations. So some people think that Big Bang was quantum fluctuation. And in this particular scenario, quantum fluctuation eventually leads you to homogeneous structure that the space becomes nice and smooth. Well, our space is nice and smooth. Originally, it was like quantum, right? There was some singularities, eventually become nice and smooth. So in this case, look very nice and smooth, but we should not be happy if our universe will be like this because it's called hit death of the universe when everything is the same. But at least you see that, well, this simulation that makes sense. It's just another example of quantum gravity. So people try to do this. Okay. Right. So let us finish. So we discuss scales of nature. And we really want to understand this triangle better. People try on LHC reach beyond electroweak scale. They use cosmological scales and reveal them back in time to Big Bang period and before recombination epoch to know again about the scales. And they found, for instance, there should be inflation and should be physically explaining inflation. And they are serious about this. People looking for black holes, they're actually looking inside stars to understand quark-gluon plasma. And theoreticians propose a very fancy theories of quantum gravity. So there is string theory. This is this quantum spin forms. This is causal dynamical triangulations. So looks mysterious. And when you read articles, it's actually hard to read the articles. I tell you the truth. I tried to understand quantum gravity in preparation. But after some moment, I stopped being able to do this. I spent quite a bit of time trying. I think need at least several weeks to get an idea how it's done properly. Now people advancing, and this is modern research. And also this Sugra is based on A7. This is some interesting mass behind. But at the very end, let me remember what ancient Greeks thought. Ancient Greeks thought that atoms, everything contains some air atoms, water atoms, earth atoms, and fire atoms. They can combine in different ways, create all the matter. That's what I discussed using statistical physics and how not exactly the same it's in reality. And ancient Greek, it was here, scale of order of meter, maybe centimeters, maybe a little bit here. They were, and we are now here. So there were 15 orders of magnitude away from modern science. And we see, well, they had some good ideas. They definitely helped science, but their perception of the world was very distant from how the world actually is. Like what they discuss looks very childish by modern science. And you know what? They're still even more than 15 scales away until Planck scale. So believe that all this crazy stuff is actually correct. Are we not better than ancient Greeks in some sense? What we are doing the same. I don't know if it's a mistake. It is, we don't have much choice. We try to extrapolate our understanding of this scale to a completely different scale. And I told you that until now, science, every 3 scales changes. So of course we cannot know if it will be the same. As it will be, of course we should try, but it's very hard to know if it will be. What we know for sure that we should try, because when we try, we come to the remarkable discoveries, which the one which cannot predict. And this always happens with science. Very often we want for something, and this something was stupid actually to want. But while we are attempting to approach it, we make very beautiful discoveries. This is part of science. That's why we like it as well. So to believe that it's the end of the story, I think it's far from the end of the story. To be pessimistic, no. We of course have to be optimistic and try, because it's leads you to a completely new way of thinking, and eventually it helps development and understanding of nature. Okay, so this is the end of these lectures. We finished events in Stockholm. There will be one more event, biophysics in Uppsala. It will be given by a professor in cell and molecular biology. So I think about this event as an anthropic principle event. So why our universe is crazy? Well, it is crazy because we are here to observe the craziness. And next time we are going to discuss why we are here from the point of view of biology. So it's kind of confirmation of anthropic principle. It will be concluding lecture of the series. I would like to thank you everybody who helped in preparation and in all senses. And I would like to remind that we aim to raise funds in support of Ukraine. So please go to our website and leave your feedback and leave your support as in a way you judge appropriate. Thank you.
Questions?
Okay, if you go back to the slide with the, I guess the big schema, yeah. So essentially, the stuff that's like to the left of this electroweak scale, I mean, where the Higgs boson is.
Yes.
So the stuff to the left of it doesn't have a mass.
So Higgs, no, what will not have mass, like electron will not have mass, and all quarks will not have mass. So Higgs boson will be in some potentially with mass, but it will, I mean, it will have what is called zero vacuum expectation value. So it can have mass, but all the matter which you care about will not have mass. Yeah. Yeah, and the challenge to understand why it has mass, actually. That's one of the challenge. Like, it's like iteration question.
Well, looking at your slide, apparently there should be many more questions than answers. We'll just leave it as this. None? Okay, so thanks, Dima, again, and See you all for next lecture.